So let me discuss examples on plane trusses. So this is the first problem for the triangular truss shown below. Cross-sectional area of the horizontal member is 625 mm square while 750 mm square for the other two members. Modulus of elasticity 200 gigapascals. Compute the nodal displacements and member forces as well as the support reactions by the matrix solutions. So this is the truss, and this truss has 3 degrees of freedom, 2 at A, rightward or leftward and downward, and there's only 1 degree of freedom at B. So all in all, we have 3 degrees of freedom, and we can easily solve this using our calculator. So we expect 3 equations, 3 unknowns also, though the structural stiffness matrix would be 6 by 6 because there are 2 expected movements at each support. So let's mark A, B, and C respectively as 1, 2, 3. So our member 1 is AB, our member 2 is AC, and our member 3 is BC. So for member 1, the cosine is, because 1 to 2 is directed down to the left, so both cosine and sine are negative to the left and downward. So cosine is negative 2.5 over square root of 2.5 square plus 6 square, and it will give us negative 5 over 13. The length of AB is 6.5 meters. So opposite negative 2.5, because it is leftward, divided by length of AB, which is 6.5, so it gives us negative 5 over 13, while the sine of member AB or member 1 is negative 6 over 6.5, so that gives us negative 12 over 13. So the stiffness of member 1, global stiffness member 1, is area E over length times quantity. Remember, cosine square CS, negative of C square, negative of CS, then CS S square, then negative of CS, negative of S square. Then we copy this 4 by 4 here, and we copy this here. So again, this is cosine square. So square of negative 5 over 13 is 25 over 169. This is the product C times S. So negative 5 over 13 times negative 12 over 13 is 60 over 169. Then this is the negative of the first. This is the negative of the second. Then this is CS. So we just copy that. This is S square. So the square of sine, 144 over 169. Then the negative of the first, negative the second. Then we copy this 4 by 4, the top left corner here, very same, and this one here, it's the same. So simplifying, involving 750 and 200,000, and the stiffness is in Newton per mm. So KEB is equal to these values here. And I mark 1, 2, 3, 4, columns 1, 2, 3, 4, then rows 1, 2, 3, 4. So that when we assemble the structural stiffness matrix later, we won't be confused. Number 2, it has cosine. Number 2 is AC, and A to C is down to the left, and that's why it's also negative. So cosine is 2.5 plus 5.5 is 8. This is 6, so the length of AC is 10, so it is negative 8 over 10, or negative 0.8. While the sine function is y, so negative 6, going down is negative 6. sine of the angle, this angle here, so opposite is 6, but it's negative over 10. So negative 0.6. The length is 10. Square root of 8 square plus 6 square is 10. Then its stiffness area 750. Then modulus plasticity 200,000. The length is 10,000 mm times the quantity c square, which is square of cosine. So 0.64. The product of negative 0.8 and negative 0.6 is 0.48. They're negatives here. Then copy CS here, 0.48. This is S squared. The square of sine is 0.36. Then they're negatives. And after that, we copy this in this corner here. We copy this in this corner. So involving the stiffness, number stiffness, and we have the stiffness of member AC equal to this value. Then for BC, B to C. So this is point 2, this is point 3. The direction is to the left. That's negative direction. Cosine of 180 or negative 1 because that's 180 degrees if we measure it counterclockwise. Then the sine of 180 is 0. So for member T, cosine is negative 1, sine is 0. The length is obviously 5.5. And substitute KBC is area 625 times 200,000 over length 5,500 times course the square of cosine is 1, then CS is 0, negative of the first, negative of second remains 0, then CS 0, S square 0, then their negative 0, 0, then here we copy this 4 by 4 here, same, then this 4 by 4 here. So simplifying, KBC is equal to 22727.27, then this is negative 22,727.27, then negative positive. By the way, BC is 2 to 3, so that would be 3, 4, 5, 6. KAC is 1 to 3, so 1 to 5, 6. Number 1 is 1 to 2, so 1, 1, 2, 3, 4. Again, for 1, the numbering for the horizontal displacement or horizontal force. 2 is for vertical at a node. Then you double that number. So 1 is 1 and 2. Then 2 is 3 and 4. And 3 is 5 and 6. Then let's now assemble the matrix. It's expected 6 by 6, but we only deal with 3 by 3 matrix after we eliminate rows and columns associated with 0 displacements. So this is it, the 6 by 6, and I shaded the portion which we do not consider because U4, the vertical displacement at B is 0. U5 is the horizontal displacement at C because this is a pin is 0. Then U6 is the vertical displacement at C, which is also expected 0. So we only consider the cells 1 to 3, rows 1 to 3, and columns 1 to 3. This unshaded column. So F1 is 0. There's no force, horizontal force at A. F2 is negative 120,000 newtons. F3 at B is again 0. So F1 again is 0. F2 negative 120. F3 is 0. So U1, U2, U3 is equal to the inverse of this matrix. So let's copy that different elements of the structural stiffness matrix. Then invert it using your calculator 3 by 3 because this is only 3 by 3. Multiplied by the forces F1 0, F2 is negative 120,000 and F3 is 0. So Solving for the displacements, u1, u2, u3 equals 22.1576, negative 19.4424, and negative 3.2 mm. The units would be in M. So for member forces, number 1, AB, that's 1, 2, 3, 4. So P1, P2, P3, P4 is equal to AE over L. So we copy this AE over L of AB times, remember, the individual stiffness is C, S, negative of C, negative of S, then 0, then the negative of the upper rows, the upper first row. Here, that's the technique. And 0, 0, 0. So because C or cosine of member 1 is negative 5 over 13, so that's negative 5 over 13. The sine is negative 12 over 13. Then these two remaining columns here would be the negative of the first two. Then the next row would be all zeros. You can remember. Then next is the negative of the upper first row. Then 0. Multiplied by the displacement u1, u2, u3, u4, where u4 is 0. So, but we have u3. Then there will be no friction forces because only the load is acting. So, in other words, this coefficient here for negative 5 over 13 times 22.1576, you distribute this row 1 here to this column. Negative 5 over 13 times 22.156 plus negative 12 over 13 times 20 times negative 19.4424 plus 5 over 13 times negative 3.2 plus 12 over 13 times 0 times this value here, that would be P1. And P2 would be 0. P3 would be the negative of P1. So because P1 is 189,090, this is rounded off, you just check it. And then P3 would be the negative of P1. So because the type of stress, whether compression or tension, is revealed by the second value. So because this is negative, so member 1 is in compression. So obviously this will be pressed downward, so that's why member 1 is in compression. Or you draw a member, then 189,090 is positive, so that means it is directed from 1 to 2 going into the direction of B. Then negative 189,090 would be going opposite to that direction, so that's why AB is compressed, or AB, member AB is in compression. Then for member force 2, P1, P2, P5, P6, so individual stiffness is this one. Then the cosine for member 2, you can remember, is negative 0.8. The sine is negative 0.6. Then the negative 0. Then the negatives of the upper first row multiplied by the displacements u1, u2, u5, u6. u5 and u6 are all zeros. So that's u1, u2, u5, u6. And negative 0.8 times 22.156 plus negative 0.6 times negative 19.4424. The rest would be 0. Then times this value here, that would be the value of the upper part. Then the lower part you just copy. So because the second value is positive, so member 2 is in tension. Then for member 3, P1, P3, P4, P5, P6 equals its value AE over L multiplied by its cosine, which is negative 1 sine 0, then the negative of cosine, negative of 0, That's it. Go to 0, then the negative of the upper part. So it's easy because P3 is the only row with value, the rest 0, displacement 0. So negative 1 times negative 3.2 times that value, that's the force in the upper row, then negative. Therefore, the member 3 is in compression because this is negative 72,727. And that's the member force of member 2. You can check using statics if it will balance. Now, to check if the truss is really in static conditions, let's solve for the reactions. Let's go back to the whole entire stiffness matrix or the structural stiffness matrix. F1, F2, F3, F4, F5, F6 are the global forces or reactions. So this is the overall stiffness for the entire truss. These are the displacements. So to solve for F4, F5, F6, because we already found F1, F2, F3, you can verify F1, F2, F3 if you multiply row 1 with this column for global stiffness matrix only. Anyway, you have to multiply just the first 3 rows because the rest will be 0. So for F4, negative 8192.99 times 22.156 plus negative 19663.18 times negative 19.4424, then plus 8192.99 times negative 3.2, and the rest would be 0. So evaluate that value. That would be the value of F4. Then for F5, negative 9600 times 22.1576 plus negative 7,200 times negative 19.4424 plus negative 22,727.27 times negative 3.2. So the answer is for F4 is, oh sorry, for F5 is 0. So F5 is the X component of the reaction at C, which is expected 0 because the only load is vertical, negative 120,000. Then for F6, the vertical component of reaction at C, negative 7,200 times 22.1576 plus negative 5,400 times negative 19.4424 plus 0 times negative 3.2, all the rest 0. So just the first two. It will give us negative 54,546. So you can check, you add all this negative 1,200. This is the vertical component at B. This is the vertical component at C. So it should be more or less 0. Then for example 2, for the bar shown below, cross-sectional area for the vertical member is 150 mm square and 200 mm square for the others. Modulus elasticity is 200 gigapascals. Compute the nodal displacements and the member forces. So if you notice, there are only 2 degrees of freedom. So the reduced stiffness matrix is 2 by 2. So it's easy. Even if we don't have a calculator, it's very easy. But if this is the problem in Theory 2, then that would be very challenging because this is indeterminate to the second degree. So first, for member stiffness, AE. So remember that only DE or EB has a unique area of 150, the rest 200. So numbering would be E is 1, then A is 2, 3, B is 3, C is 4, B is 5. So member 1, its stiffness, its cosine rather, is negative because it is directed from 1 to A, 1 to 2. It's going up to the left. So cosine is negative to the left, while sine is positive up. So cosine is 1.5, negative 1.5 over, so that's 1.5. This is 2 meters. So the length is 2.5, or in other words, the slope is 3 horizontal, 4 vertical, then 5 hypotenuse. But the cosine of EA, or member 1, because it is directed up to the left, so the fact that it is to the left is negative. Negative 3 over 5, or negative 0.6. The slope is 3 over 5. For the sine, it is upward, so it is 2 over 2.5, or positive 0.8. The length is 2.5 meters, square root of 1.5 square plus 2 square. 1.2 plus 0.8, so 2 square. So 2.5. Therefore, the stiffness of member EA is area 200. E 200,000 divided by length 2,500 times quantity C squares CS negative of C square, negative of CS S square, the negative of CS, the negative of S square, then the rest it's easy to copy. So C square is 0.36, CS is negative 0.48, CS negative 0.48, then S square is square of 0.8, so 0.64. So there's no need to explain the rest because that's very easy to remember. You just copy, right? Then involving this 200 times 200,000 over 2,500, the stiffness of member EA is equal to this. So you have to verify this value times 0.36, that should be that value. This value times negative 0.48, that should be that value. Then copy. Then this value times 0.64 should be this value. Then follow the guide, which is you make the negative of the first two rows, negative of the second two elements, then you copy, you cross they have the same elements. So remember member one is 1, 2, 3, 4. Then for member 2, EB, so the cosine is 0 because E to B is upward, and the sine is, because it is upward, the sine is 1. Or cosine of 90, let me assign an angle if you are still confused. So you have to review your trigonometry. Then the length is, of course, 1.2. So AEA is, its area is unique, 150, 200,000 over length, 1,200. Then C square, 0. CS, so 0 then negative of the first row, then CS 0, S square, so 1, and 0, negative 1, then copy. So PAA is simplifying. You have the value 0, everything in the numerator, then only have values here. So 25,000, negative 25,000, negative 25,000, 25,000. For member TEC, its cosine is positive because it is up to the right. So both cosine and sines are positive. The cosine is the slope, by the way, 1, then 1.2. We can change it to 5 horizontally, 6 vertically. So the hypotenuse is square root of 61, square root of 5 square plus 6 square. So the cosine is positive 5 over square root of 61. The sine is 6, also positive, because EC is up to the right. So 6 over square root of 61. The length is square root of 1 square plus 1.2 square, so 1.56205 meter. Then its stiffness, area, modulus of elasticity, then divided by length. times C square, so 25 over 61. CS is 30 over 61. Then there are negatives here. Then this is CS, 30 over 61. This is S square, so 6 over square root of 61 square is 36 over 61. Then there are negatives. Then copy, and you also copy this here. Simplifying, AEC equals these values. So you just verify them. By the way, E to C is 1, 2, and this is 3. Sorry, 1, 2, 3, 4. So 4 times 2, 8. So 1, 2, 7, 8. So 1, 2, 7, 8. 1, 2, 7, 8. Then finally, for member ED, D is marked 5, and therefore it is 1, 2, 9, 10. So member 4, ED. The cosine, by the way, is 3 horizontal. It is up to the right, so positive both cosine and sine. 3 horizontal, 2 vertical. So the length is square root of 13. And square root of 13 is 3.60555 meters. So cosine is x over hypotenuse. So x is 3, hypotenuse is square root of 30. Sine is y, 2, upward over square root of 30. Then its stiffness is area, 200, modulus of elasticity, 200,000, divided by length, times c square, square of 3 over square of 13 is 9 over 13. Then c times s, so 6 over 13. Then the negatives, this is cs, and this is s square, so 4 over 13, square of this. Then their negatives, copy, copy. Simplifying, a of ed would be equal to these values here. So kindly verify. Then it is bounded 1 to 9, 10, 1 to 9, 10. Although this is 10 by 10, but again, we only consider this node here, which has 2 degrees of freedom. All the rest have 0 displacements, 0 x and y, 0, x and y 0. So after we eliminate rows and columns associated with 0 displacement, it will reduce to 2 by 2. So that's the explanation. Unless otherwise you're required to compute for the reactions, then after you solve for the unit displacements, you have to set up the entire 10 by 10 matrix, because it is only there where we can see the reaction forces. So 1 and 2, the forces are F1 equals 120 cosine of 30 positive, so 120,000 cosine 30. F2 are both downward, so we have negative 80,000, and the component of 120, which is negative 120,000 sine 30. Simplifying, F1 equals 103,923.05 newtons, and F2 is negative 140,000. Then we assemble the 4 by 4 matrix, 1, 2, and 2. So this is it. So how to get this N3 here? It's 1, 1, the sum of all force coefficients in row 1, column 1. So we have 5,760. And let's look for the others. We have 1, 1 here, 0, plus 0. We have 1, 1 here, 100. We have 10,494.83. Then we have another 1, 1 here, 7,680.467. So adding those, 5,760 plus 10,494.83 plus 7,680.467, we have 23,935.297. For this entry here, this is row 1, column 2. Row 1, column 2, we have negative 7,680. Row 1, column 2, that's 0. Row 1, column 2 plus 12,593.79. Then row 1, column 2 plus 5,120.311. It will give us 10,034.101. Since this is 1, 2 by symmetry, you just copy. The resulting reduced stiffness matrix will always be symmetrical. Then this is 2, 2. So add 2, 2, we have 10,240, 2, 2. Then plus this is 2, 2, 25,000 plus 2, 2, 15,112.55 plus 3,413.541 will give us 53,766.091. So solving for U1, U2, it is just the inverse of this 4 by 4 matrix times this force matrix here. And we can now solve for U1 and U2. So the inverse of this matrix, 4 by 4, 2 by 2, then times this matrix here, the force matrix, then U1, U2 can now be solved. So U1, U2 equals in mm 5.894594 mm and negative 3.703951 mm. Then for the force, member forces, so let's show them next slide. So member 1, P1, P2, P3, P4, we have its stiffness, area, length over, area modulus of elasticity over length times C, its cosine, its sine, then negatives, second row 0, everything, then the negative of the first row, and 0, everything for second row, multiplied by the displacements U1, U2, U3, U4, where U3, U4 are all zeros. Then there will be no fixed forces. So negative 0.6 times 5.894594 plus 0.8 times negative 3.703951 times this value here, because we have 0, 0 here, 0.6 times 0 minus 0.8 times 0, which will be 0. So the result would be, you just copy or evaluate the upper or the first row value. Then for the third row, you just make it negative of the first row. So negative 103,739 newtons, and this is 103,739 newtons. You always look at this. So that member will be in tension because this is positive. Or in short, the meaning of that is, just imagine the member is directed from left to right. So at the left, it's negative, so it's leftward. At the right, it's positive, so it's rightward. So the member is being stretched. That's why the sense or the force of axial load of that member is tension. So that's member EA. For member EB, so it's area 150 to 100,000 over length 1,200. Then the cosine is 0, the sine is 1. So it's easy to remember. So cosine 0, sine is 1, then negative of the first, then 0, 0, 0, then negative of the first row, and 0, 0, 0, times the displacements U1, U2, then 0, 0, because U5 and U6 are all zeros. So it's 0 times 5 point something, 0. 1 times negative, so negative times this value. So the first value after is negative, and the third row is positive. So number 2 is in tension. EB is in tension. Next, member 3, P1, P2, P5, P6. And area 200,000 over its length. Then cosine, sine, negative of cosine, negative of sine, 0, 0, 0, and simplify. That's just like just like what we did in the upper part. Then you'll get 237,680 negative 23768. So member 3 or member EC is in compression because that's negative. And lastly, member 4, P1, P2, P9, P10, or member ED, area 200,000 over its length. Then the cosine of that member 4 is positive 3 over square root of 13. The sine is 2 over square root of 13. Then they're negative 0. Then make the third row would be the negative of the first row multiplied by the displacement u1, u2, and 0, 0. Then simplifying, you'll get 31,618. So negative 31,618. So member 4 is also in compression. So that's it. So let's have example 3. This example, the degree of freedom is 5 by 5. So our calculator cannot be used here in inverting the 5 by 5 matrix. So instead, you'll have to use Excel. This is example 4.8 of your handouts. Determine the nodal displacements and the support reactions. E is 200 gigapascals. So that's the truss. Then for first, let's have the member stiffness, individual stiffness matrix. So for member 1, we choose U1, L1 as member 1. So its cosine, this is going down from 1 to 2. So its cosine is 0, while its sine is negative 1. So remember that sine of an angle that the member makes with the horizontal is negative 1. Or you may denote an angle, it is negative 90 degrees, sine of negative 90, or sine of 270 degrees from the positive x-axis. So for counterclockwise, 270, sine of 270 is negative 1, or for clockwise, sine of negative 90. So that's why it's negative 1. The length is 4, as shown in the figure. So K1 is the area of the member, 200, then modulus plasticity, 200,000 megapascals divided by length, 400, then times cosine square, CS, then their negatives, can remember, so 0, C times S is 0 also, so they're negative 0, then CS 0, this is sine square 1, and the negative of this 2, 0, negative 1. Then after that, copy this 2 by 2 matrix. I correct it because in the preceding slides, I usually mentioned 4 by 4. So it's 2 by 2 here. Then this 2 by 2 matrix also here. Then for member 2, which is this member here, bounded by 1, 1, 2, 5, 6. Member 1 is 1, 2, 3, 4. So considering this AE over L, multiply all this by AE over L, the result will be this. Then for member 2, the cosine it is down to the right. So the cosine is, because the slope is 6 horizontal, 4 vertical, so that means 3 horizontal, 2 vertical. So positive 3 over square root of 13 cosine. The sine is negative 2 over square root of 13 because the direction from 1 to 3 is down to the right. So to the right for cosine, for x, so positive, then for sine, negative. The length of that member is square root of 13, or in decimal, square root of 6 square plus 4 square, so it's 7.2111 meter. Then K2 is equal to area 300 E 200,000 over length. So this is the length, then quantity 9 over 13 for cosine square for CS negative 6 over 13, then their negatives, then this is CS, you just copy, S square is the square of negative 2 over square root of 13 is 4 over 13, then their negatives here, then copy that, and then member 3, so K2, considering this value here, would be equal to these values here. So 1256. Number 3 is 2 to 3. So 3, 4, 5, 6. That's the numbering. Then because number 3 is just to the right, so the cosine is 1 and the sine is 0 for member 3. The length is 6 meters. So we have 1, 0, negative 1 cosine square. So 1, CS 0, then negative 1, 0, then CS 0, S square 0. So everything is 0 here, then copy. So considering the value 300 times 100,000 over 6,000, then that would be this is 10,000, negative 10,000, then negative 10,000, 10,000. Number 4 is 1278. Number 4, the cosine, it is directed down to the left. So the cosine is negative, the sine is negative. So the cosine is negative 3 over square root of 13. The sine is negative 2 over square root of 13. The length is 7,000 or 7.2111 meters, just like number 2. Then K4 is area, 200,000 over length times quantity cosine square, so 9 over 13. CS is 6 over 13, they're negatives, then CS 6 over 13, then sine square 4 over 13, then they're negatives, then copy this 2 by 2 matrix here, copy this 2 by 2 matrix here. So that's K4. So multiplying all these terms or values by 300 times 200,000 over 7211.1, then the results will be this. Number 5 is 2 to 4, so it's going left, so its cosine is negative and its sine is 0, the length is 6 meters. So here we go for member 5. So because the stiffness of member 5 is almost the same as member 3, then the cosine is negative 1, so of course its square is positive 1, then its sine is 0, so the form of stiffness would be the same, except for member 5 is 3, 4, 7, 8. 3, 4, 7, 8. So it's the same. This is K of member 5. Then for members, I think everything is finished. So we now assemble the structural stiffness matrix or the global stiffness matrix. The forces are, at 1 we have 60,000 newtons, then 0 for 2, F2 vertical, for 3, 0, but for F4 is negative 100,000 again. F5 horizontal force at 3 is 0. F6 is unknown, the vertical reaction at 3. Then F7 is the horizontal reaction at LO, so it's unknown. Then F8 is the vertical reaction at LO. Then for the global stiffness matrix, so we have 1, 1 here. 1, 1. So we add for K1, it's 0. For K2, we have 5760.35. For K3 is none. K4, we have another 5760.35. Then K5 is none. There's no 1, 1 here. So it's only 0 plus K2 5760.35. We have 1, 1 here. Then K3 none. K4, then we have 1, 1 again, 5760.35. Then K5 none. So it's 11520.7. Then 2, 1, 2, 1. So 2, 1, we have 0 here. For 2, we have negative 3840.23. Then for K3, 2, 1, there's no 2, 1. K4, 2, 1, plus 3840.23. And K5, none. So negative 3840.23 plus positive 3840.23, that's why it's 0. Then 3, 1, 3, 1. It's 0 here. There's no 3, 1 here. There's no 3, 1. There's no 3, 1. There's no 3, 1. So it's 0. Then, by the way, this is 1, 2, row 1, column 2. So that's why it's also 0 here. Remember that the global stiffness matrix is symmetrical. Then 0, 0 here. Then for row 1, column 4, 1, column 4, it's 0 here. There's none here. There's none here. There's none here. There's none here. So that's why it's 0. Then that's why it's also 0 here at 1 at 4, 1. Then at 1, 5, this is 1, 5, none, 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 then none. It's only here. Row 1, column 5, negative 5760.35. And this is also negative 5760.35. Then I want you to fill up the rest. So verify that these are the values. I will just concentrate on this 5 by 5 matrix because there are 5 degrees of freedom in our truss here. So we'll just concentrate on this, and because we're going to invert this 5 by 5 matrix also. Then 2, 2, we have 10,000 here. Then plus 2560.16, there's none. Plus 2560.16, then none. So that gives us 15,120.32. This is 2, 3, row 2, column 3. So 2, column 3, it's 0 here. 2, column 3, none. 2, column 3, none, none. 2, column 3, none. So that's why it is 0. So 3, 2 is also 0. This is 2, 4. 2, 4. Row 2, column 4. So we have negative 10,000 here. There's no 4 here, so none. 2, 4, none. 2, 4, none. 2, 4, none. So it's negative 10,000. So that's why in 4, 2, it's also negative 10,000. This is 5. This is 2, 5. 2, 5. There's none here. Here we have 2, 5. 3840.23. None, none, none. So it's 3840.23. 5, 2 is also 3840.23. Then this is 3, 3. 3, 3. So we have 3, 3, 0. Here there's none. Here we have 3, 3, 10,000. Then here none. Here another 10,000. So 10,000 plus 10,000, it's 20,000. Then this is 3, 4. 3, 4. Row 3, column 4. So 0, there's none here. 3, 4, it's another 0 here. And here 3, 4, it's 0. So it's 0. So 4, 3 is also 0. Then this is 3, 5. There's none here. There's none here. Here 3, 5 is negative 10,000. Here none, none. So negative 10,000 for 3, 5. 5, 3 is negative 10,000 also. 10,000. 3, 5 is negative 10,000. So 5, 3 is negative 10,000. Then 4, 4. This is 4, 4. 4, 4. We have 10,000 here. None. 0. So far 10,000. None. 0. So it's 10,000 for 4, 4. And this is 4, 5. None. None. 4, 5. 0. 4, 5. None here. So 0. Then 5, 4 is also 0. Finally, 5, 5. We have 0. We have 5760.35 here. Then we have 10,000 here. 5, 5. Then none here. So none also here. So 5760.35 plus 10,000 is 15,760.35. So that's it. Then complete the rest. And remember by symmetry to facilitate the filling up of these cells. So since this is 5 by 5 and it will take time if we're going to manually invert this 5 by 5 matrix, but of course I will not do that for your quiz or your quiz, but for your assignment maybe, because you can use Excel for that case. Then let's now compute U1, U2, U3, U4, U5, which is equal to the inverse of this 5 by 5 matrix multiplied by this force matrix. So we'll do this by using, so this is the board clip from Excel. So this is the 5 by 5 matrix, and this is the force matrix in column. So we're going to multiply the inverse of this 5 by 5 matrix with this column matrix. So for this 5 by 1 matrix, so you have to equate this, write a function. So we have to multiply the inverse of this first array from A1 to E5 with this column matrix at F from F1 to F5. And hold down control and shift, then press enter, and you will get these values here: 15.70798, then negative 35.2799, 10.49996 for U3, then U4 negative 45.2799, then U5 20.999992. That's it. So let's solve for the reactions. Let's solve for F5, F6, and F7. For the member forces, I will leave that to you. So this is the global stiffness matrix. So to solve for F6, you have to multiply this row with the values here. So these are the Displacements, global displacement. So 3840.23 times 15.70798 plus negative 2560.16 times negative 35.2799. Then 0 plus 0, then negative 3840.23 times 20.99992. The rest is 0, so compute that. So we have F6, F7 would be equal to, for F6, 70,000 newtons. Then for F7, negative 5760.35 times 15.70798 plus negative 3840.23 times negative 35.2799 plus negative 10,000 times 10.49996, then 0, 0, 0, and the rest also will be 0. So that's negative 60,000. Then F8, negative 3840.23 times 15.70798 plus negative 2560.16 times negative 35.2799, and the rest is 0, so that's it. So you'll get 30,000. So F6 is the vertical component at L2, so 70,000. F7 is the horizontal component at LO, so which is to the left, which opposes the 60,000 Newton load to the right, which is correct if you sum up forces horizontal. Then the vertical component at LO is positive 30,000 upward. So this is also upward. The total upward reactions is 100,000, which is equal to the downward load, which is 100,000 newtons. So check. Then let's proceed to example 4.9. The truss shown below undergoes support movement at node 4 of 3/8 inches to the right. In addition to the applied force of 5,000 pounds, find the final bar forces by a technique suggested by the author, which is when a displacement is introduced from the principle on bars. When a displacement is introduced at node K or N, then we have to change the value of the stiffness at that cell, K and N, by multiplying it by a very large number. Then the force value at the same level is replaced by the stiffness, original stiffness of that cell times the very large value times the specified displacement. So you can recall the principle when there is support or nodal movement. Then the second one is using the matrix partitioning technique, or we call it by expansion of rows, so which is the same. So all areas 1 square inch, and E is 10 times 10 to the 6 psi. So this is the truss, which is supposedly 2 by 2, 2 degrees of freedom here, but because there is specified displacement here, this may be 3 by 3 if you use the second, if you use the first technique. But if you use the second technique, this will only be 2 by 2. So I will present first the second part, which is matrix partitioning technique or by expansion. But before that, let's select this as one. There are already numbered numbers presented. So this is member 1, member 2, member 3. So for member 1, the cosine, because this is up to the left, so cosine is negative. The slope is, we have 3 and 6, so 1 and 2. So the slope is 1, 2, square root of 5 would be the hypotenuse. So cosine is negative 1 over square root of 5. the sign is because the member from 1 to 2 is upward, so it is positive 2 over 5, 2 over square root of 5 rather. Then the length is square root of 3 square plus 6 square. Convert that to inches, so 36 square root of 5 inches. So for A1, it is area 1 times 10 to the 6, 10 to the third. So let's make the stiffness kips per inch this time, kips per inch. Then square of cosine is 0.2. Then product CS is negative 0.4. Then their negatives. Then CS, copy, negative 0.4. This is S square. 2 over 5, 2 over square root of 5 square is 4 over 5 or 0.8. Then their negatives here. Then copy this 2 by 2 matrix in this bottom right corner. Then this 2 by 2 matrix in the top right corner to bottom left corner. So combining this value here, multiply everything, the values of the cells here. So we have K1 equal to this. So you have to verify. Number 2 is cosine 0, then sine is 1. Because it is 1 to 3, 1 to 5, 6, and it's upward only. Sine is 1. Then length is 6 times 12, 72 inches. So substitute K2, 1 times 10 times 10 to the 3 over 72 times quantity 0, 0, 0, 0. Then 0 sine square is 1. Then their negatives. Then negative of row 1, or copy this 2 by 2 matrix here. This 2 by 2 matrix here. So combining with 10 times 10 to the 3 over 72, that would now be the results. Number 3, cosine is, this is up to the right, so its cosine is the positive of cosine for member 1, because they have the same slope. So positive 1 over square root of 5, sine is 2 over square root of 5, the length is the same, 36 square root of 5. So K3 is 1 times 10 to the third over 36 square root of 5 times cosine square is, this is cosine square is 0.2. Then CS is 0.4. Then their negatives, copy CS. This is S square, so 0.8. Then their negatives. Then copy this 2 by 2 matrix here, this 2 by 2 matrix here. So we have K3 combined with this value equal to that. Then for the global stiffness matrix, we have 8 by 8 supposedly, but we do not consider all the 8s because this is supposedly by technique A, this is 3 by 3 only. So that's why I have to cover, or I have to emphasize only those needed cells, which is 1, 2, and because the specified movement at 4 is 3/8 inches to the right, so that is 7, number 7, or its numbering is 7 because the vertical is 8. So we only fill up one, this 2 by 2 matrix and the 7, 1, 2, 7. Okay. So 1, 1 is, we have 24.8452 plus 0 plus 24.8452. So that's 49.6904. This is 1, 2, row 1, column 2, negative 49.6904. 1, 2 here is 0, then 1, 2 here is positive 49.6904, so that makes it 0. Then 2, 1 also is 0. Then
For this cell here, this is row 1, column 7. 1, column 7, there's none here, there's none here, then it's only here. Row 1, column 7, negative 24.8452. Then 7, 1 is also negative 24.852 by symmetry. Then let's proceed to this, 2, 2. 2, 2, we have 99.3808 plus 138.8889 plus 99.3808. So adding them, we have 337.6505. This is 27. There's none here. There's none here. So only here. 27, negative 49.6904. Which is that. So 72 is also negative 49.6907. And finally, 77. There's none here. There's none here. Only this one. So copy 24.8452. So we have a 3 by 3 matrix. Then remember that uh, displacement is specified at this cell here, 24.8452. So we change this by technique number, ano, because we have to partition first, we eliminate rows and columns associated with zero displacement. So because these are all zeros, that's why we do not consider this shaded portion without value. So supposedly this is my technique, but actually if you're going to expand it, this technique, if you expand rows 1 and 2, this is similar to partitioning technique. Actually, it is similar to partitioning technique. So we have to put the unknowns in the upper rows, then the knowns in the bottom rows. So if you partition this, it's like expanding rows 1 and 2. So we have 5, 0. This is the 2 by 2 matrix. Then this matrix here times 3 eighths. So U1, U2 plus these two, negative 24.8452, negative 49.6904 multiplied by this cell. This is 2 by 1 and this is 1 by 1. So that's it. So when you expand, it's like partitioning. So the same results would appear. So that this force matrix, by the way, 5, we have 5,000 here. So we have to express the load to keep. So 5,000, then along y, there's none, so 0. So this is negative 24.8452 times 3 eighths. So when you transpose it to the left, it becomes positive. So plus 5 plus whatever is the product. Then 0 plus, because this is negative, it becomes positive. So 49.6904 times 3 eighths. So the upper load becomes 5 plus 24.8452 times 3 eighths. So it becomes 14.31695. The lower load is 0 plus 49.6904 times 3 eighths. So 18.6339. Then this is the original matrix, then U1, U2. So solving for U1, U2, it is the inverse of this 2 by 2 matrix times this force matrix here. So the result would be 0.288123 and 0.055187 for U2 inch. So that's the resulting displacement. Then for the techniques suggested by the author from numerical methods, so the a displacement specified at 7 is, this is 7, is 3 eighths. So the cell originally here, the value here is multiplied by a very large number, and that very large number is, as suggested, is 1 times 10 to the 10. So original value, which was 24.8452 times 1 times 10 to the 10, so it becomes 2.48452 times 10 to the 11. Then the force value here is equal to this value here after we multiply a very large number times the specified displacement. So multiplying this by 3/8, it becomes 9.31695 times 10 to the 10. So after that, we have to solve this 3 by 3, invert this 3 by 3 matrix. So U1, U2, U7, of course, we expect U7 to be 3/8 or 0.375 also. So it is the inverse of this matrix times this force matrix. So U1, U2, U7 equals the inverse of the matrix using your calculator because this is just 3 by 3 times the force matrix, which is 509.31695 times 10 to the 10. Solving for U1, U2, U7, and we have 0.288123 and 0.055187 and 0.375. As for U1, U2, it's the same as the first technique. So we now solve for the member forces. For member 1, P1, P2, P3, P4, it is equal to uh, the value 1 times 10 to the third over length times cosine square. So for member 1, remember, cosine rather, for member 1, remember it was negative 1 over square root of 5. For each sine 2 over square root of 5. They're negatives, then 0, then negative of row 1 is copy, then 0. Multiplied by the displacements, U1 0.288123, then 0.055187, then U3 4 zeros, then expand. Then negative 1/5 times 0.288123 plus 2 square, negative 1 over square root of 5 rather, times 0.288123 plus 2 over square root of 5 times 0.055187. The rest is 0. Then times 10 to the 10 times 10 to the third divided by 36 over square root of 5. It will give us negative 9.875. Then second one is 0. Then the negative of the upper is 9.875 positive. So therefore, member 1 is in tension. Keeps in tension. Member 2, P1, P2, P5, P6. Remember the cosine is 0, the sine is 1. So area 1 times E 10 times 10 to the third kips per inch square divided by length 72 inches multiplied by its cosine is 0, sine is 1, then their negatives 0, negatives of row 1, then 0. Multiplied by stiffness, by displacement 0.288123.055187, then 0, 0. So we have 0 plus 1. So we only have this value 1 times 0.055187 times 10 to the third over 72. So 7.6650 negative 7.6650 keeps. So compression because the second value is negative. That's member 2. For member 3, P1, P2, P7, P8, then it's 10 times 10 to the 3 divided by 36 square root of 5 times the cosine was 1 positive 1 over square root of 5. The sine was 2 over square root of 5. So 1 over square root of 5, 2 over square root of 5 over square root of 5. Then their negatives, then 0, then the negatives of row 1 multiplied by quantity 0.288123.055187. 3/8 is specified and 0. So we have to expand these 3 rows because the last is 0. Times 10 times 10 to the 3 over 36 square root of 5. So you'll get 1.3050 negative 1.3050. That skips also compression. So member 3 is in compression also. So the next example considers two movements. So the truss shown below undergoes a support movement at node 1 of 7.6 mm to the right and settlement of 15.25 mm at node 4, or this is 8, negative 15.25 mm. In addition to the applied force of 133.5 kilonewtons. So find the final bar forces by a technique suggested by the author, and letter B using the matrix partitioning technique. All areas are 1,290 mm square and modulus of elasticity 200 gigapascals. Let's set up number 1. It's already indicated the figure. So verify the member stiffness. So because we already solved the individual stiffnesses in more detail from the previous examples. So this time, it's up to you have to verify. And you have to practice so that you will know, you will learn. So K1, you have to verify that it is equal to this. The cosine is 1 over square root of 2. The sine is also 1 square root of 2 from 1 to 2. So these are the values. Then K2, verify that these are the values. Number 2 is 1 to 3, 1 to 5, 6. The slope is 6, 3, so 2 horizontal, 1 vertical, square root of 5. So the cosine is 2 over square root of 5, the sine is 1 over square root of 5. Then multiply by area E over length, then show that these are the values. K3, number 3 is just horizontal. The cosine is 1, 1, 2, 7, 8. So cosine is 1, sine is 0. So that's why there's only value here, 1, 1, and 1, 7, 7, 7, then 7, 1. K4, number 4, is horizontal, so it looks the same as this, except that the length is 3. So 3, 3, 4, 5, 6, because it is 2 to 3, number 4. Then number 5 is 3 to 4, the cosine is positive, the sine is negative. So K5 show that that's the stiffness of number 5. And lastly, number 6, 2 to 4, that's 3, 4, 7, 8. 3, 4, 7, 8. So verify that this is the stiffness of number 6. And this is the global stiffness matrix. So you add 1, 1, everything 1, 1 here. This is 1, 2. So you add, because we already have this process in the preceding slides, and so on and so forth. Then we shade or eliminate rows and columns associated with zero displacements, which is U2. U2, U1 is specified 7.6 to the right. U2 is not specified or it is 0. Then U7 also is 0 because U8 is negative 15.25. So we eliminate rows 2, column 2, and row 7, column 7. So leaving the matrix to be 6 by 6. Because it is 6 by 6, applying the of technique from numerical methods, so it will take very long time to invert the 6 by 6 matrix. So we use Excel again here. So this is now the reduced stiffness 1, 3, 4, 5, 6, and 8. So 2 and 7 are removed. And unknowns, the unknowns are U3, U4, U5, U6. Then, because specified displacement is introduced at 1, then we have to change the value of the cell here by multiplying it by a very large number. So it becomes 8.98406 times 10 to the 14. Then the first value at 1, is this cell value here times the specified displacement of 7.6 nm. So that's why it becomes this value 6.8278821 times 10 to the 15. Then another specified value is introduced at 8. So the original cell value here at 8, which was 38097.67, is multiplied by a very large value, which is this. So times 10, 1 times 10 to the 10, it becomes 3.80977 times 10 to the 14. Then the force value is multiplied further by the specified displacement of negative 15.25. So this cell value times negative 15.25, it becomes negative 5.809894 times 10 to the 15. So this is now the result of changing the cell value at specified displacements and the force values. So this is 6 by 6. To solve for the displacement, we invert this 6 by 6 using Excel multiplied by this force matrix here. So this is the clip from Excel. This is the 6 by 6 matrix here. And this is the force value or force matrix. So in this cell here, we want to compute these displacements. So we have to define a function here, which is the multiplication of this, the inverse of this matrix times the second matrix here. So that's why we have inverse of B2 to G7. Then the inverse of that, and this column matrix, which is A2 to A7. So hold down Control and Shift, then press Enter. You will get this global displacement 7.6 as the original given value. Then U3 8.2148374, U4 negative 0.252518, then U5 8.559 8.5991351, then U6 negative 9.215639, then U8 same negative 15.25. Then let's solve this by partitioning technique. So we first write the rows of unknown displacements U3, U4, U5, U6. So we have to change then the specified displacements. So 7.6, U2 is 0, then U7 is 0, then U8 negative 15.25. These are this. So unknowns, the upper rows unknowns, and the bottom rows the knowns or the specified displacement. So we divide this here. So that's the partitioning. So this forces here is equal to this stiffness multiplied by this unknown displacements, then plus this 4 by 4 matrix times this specified displacement. So therefore, we can compute the product of this stiffness and this known displacement matrix. Then we transpose them to the right to have these values here change. So these are now the new global forces after we multiply or after we expand. So for example, in this row here, this is 0, Then if we expand this, negative 330,405.592 times 7.6. So that's negative. Plus negative 30,405.6 times 0. This times 0. So 15,384.1477 times negative 15.25. So the expansion is negative, then transpose to the left, 0 plus positive value, it becomes 465,690.75. So for the next force matrix here, which is this one, this is equal to 0 because the product of this and this is negative. When you transpose, it becomes positive. So 0 plus 30,405.592 times 7.6, then 0, 0, then another, so minus, no? Minus because this is positive. So minus 7692.0738 times 15.25. So the result will be this. You have to check. Then for row 3, it is 0, then plus, because this is negative, then plus again, because this is also negative. When you transpose, it becomes positive. So that's why you get 697,524.31. Then finally, for this last row here, row 4, negative 133,500 plus 15,384.148 times 7.6, then minus 30,405.592 times 15.25, because that's positive. So the result is negative 480,265.75. Then this is the reduced stiffness matrix 3456, which is this, times the unknown displacement. So solving for this unknown displacements, it is the inverse of this 4x4 matrix times this force matrix, global force matrix. And again, we invert this by using Excel because this is 4x4. It will consume our time doing that. So this is it. So we define this cell here. This is equal to the product of the inverse of this 4x4 matrix and this matrix here. So you get the same results for U3, U4, U5, and U6. So this is the procedure, and that's the result. So therefore, for member forces, I will only compute, or let's have a representative example for member 1. So this is the stiffness times the cosine of member 1 is 1 over square root of 2. The sine is 1 over square root of 2. The negatives, then row 2, 0, everything. Then the negatives of row 1 and 0 times the displacements. U1 is 7.6, U2 is 0, then U3 8.214836, U4 negative 0.25252. So expanding as before, you'll get negative 15,580 and 15,580. So member 1 is in tension because this is positive 15,580. So that's it for this problem here. For member, then this is our last example. Let's have here fabrication error and temperature change. So let's combine it here so that we'll only have one example. But in some cases, we only compute displacements due to fabrication error and separate temperature change. So here I combine the two, but I explain it well here in more details. Compute the nodal displacements member forces and component reactions for the truss shown below having the conditions that member 1 is fabricated 10 mm too long. Member 4 is subjected to a temperature reduction of 20 degrees Celsius, and member 5, which is this member here, is subjected to a temperature increase of 40 degrees Celsius. Cross-sectional areas in mm square are enclosed with parentheses. The areas are given. The member designation is also provided. E is 200 gigapascals and beta is 11.6 times 10 to the negative 6. For fabrication error, delta is from the formula, delta is PL over EE. So if you solve for the force, this is for the fixed end force. It is AE over L times delta. So if delta is positive, then because we multiply this by 1, negative 1. So if delta is positive, then the member should be subjected to fixed end force, and that member is in compression. So treat delta positive for too long and negative for too short. So equivalent fixed end force along the axis of the member would be that value multiplied by 1, negative 1. So because the second value is negative, if delta is positive, it is in compression. The fixed end force will be compression. But the equivalent nodal forces would be opposite to compression, so that would be in tension. So if error is too long or positive, the fixed end force is such that it will be compressed, but the equivalent nodal force will be opposite to compression, so tension. So this is the fixed end force. Fixed end forces as a result of this, so it is in compression, but the equivalent nodal forces would be tension opposite to that. So that's why it's tension here for member I, and member I is directed from end to end. Then we resolve these forces into components. To resolve that into components, we have to use the slope of the member, which is this. So equivalent nodal forces, then this is equivalent nodal forces, so that it will be, the components will be parallel to the global system. So we resolve the force P into x and y components. So Py, which is equal to P sine of this angle, theta, and Px, P cosine theta. So this is now the equivalent nodal forces. So we have to resolve this P into components. So remember that it should begin with the fixed end force. So positive, negative. So the result would be compression. So remember that fixed end forces and nodal forces are opposite. So if in the fixed end forces it's compression, for the nodal forces it will be in tension, as shown. So Px is plus minus P cosine theta depending on the direction, and Py is plus minus P sine theta depending on the direction. The same principle applies to thermal temperature changes. So we have to multiply the fixed end force, which is given by beta delta T times area E, where delta T is positive if the temperature is increased, then negative if the temperature is reduced. So fixed end forces along the axis of member would be beta delta T AE after we multiply 1 and negative 1. So the denominator will also be negative. So if the delta T is positive, then the member will be subjected to fixed end forces, which is in compression. Then the equivalent nodal forces is such that the member will be in tension. So it's very the same principle. So the same calculations and directions as above. of forces as shown above. So member 1, for this case, which is 1 to 2, it is down to the left. So both cosine and sine are negative. So for the cosine, it's x movement divided by length. So the x movement is negative 8 because the length of member 1 is square root of 8 square plus 6 square. This is 6. So 10, the length is 10. So negative 8 over 10 is negative 0.8 for the cosine. For the sine, it's negative 0.6, negative 6 over 10. The length is 10 meters. So area is 1,500. So K1 is 1,500 times E 200. I use 200 here, not 200,000. Let's express the stiffness in kilonewton per mm this time. So that would now be in kilonewton per mm. So area 200 divided by 100, divided by 10,000, the length of member 1, multiplied by the square of cosine 0.64, then CS 0.48, the negatives, then this is CS 0.48, this is S square, which is 0.36, then their negatives, and copy this 2 by 2 matrix here, this 2 by 2 matrix here. Then combined with this value, then K1 would be equal to these stiffnesses here. So that is stiffness K1. Remember that the unit is kilonewton per mm this time. We want the force to be in kilonewtons. Then member 2 is this one. It is 3456. Member 2 is 3456. The cosine is 0. The sine is positive 1. Then member 3 is 1 to 3. 1, 2, 5, 6. The cosine is negative 1. The sine is 0. Member 4 is 1 to 4. It is 4.5 down to the right. So cosine is positive. Sine is negative. The cosine is 4.5 over the length. The length is square root of 4.5 square plus 6 square. That's 7.5. So the slope is 3 horizontal, 4 vertical. So the cosine is positive 0.6. The sine is negative 0.6. Then for member 5, 2 to 4, 3, 4, 7, 8. The cosine is 1. The sine is 0. Then for member 6, 3 to 4. So 5, 6, 7, 8. The cosine is positive. The sine is negative. So the cosine is 12.5 divided by the length, which is square root of 12.5 square plus 6 square. We will know that later. Then the sine is negative 6 over square root of 12.5 square plus 6 square. So member 2, cosine is 0, sine is 1. As mentioned, the length is 6. So K2 is area E over length times 0, 0, 0, 0, then 0. S square is 1, and their negatives. Then copy and copy. So simplifying or multiplying all these elements with this value here, that's the result. Number 3, cosine is negative 1, sine is 0, then length is 8 meters. A3 is 1,000 times 200 over 8,000 times 1, 0, negative 1, 0, CS 0, S square 0, then their negative 0. And after that, copy, copy. Combined with this value, so K3 would be equal to the values here. And number 4, cosine is 0.6, sine is negative 0.8, length is 7.5. So K4 is 1,200 for the area, E over length times 0.36, negative 0.48, CS is negative 0.48 for negatives, then CS is negative 0.48, S square is 0.64, and their negatives, then copy, copy. So K4 with this value, AE over L, into the 4 by 4 matrix would be that result. Number 5, cosine is 1, sine is 0. length is 12.5 meters. So K5 is equal to area E over length times 1, 0, 0, 1, 0, negative 1, 0, and CS 0, S square 0, there negative 0, 0, and copy, copy. Then distribute the constant, and we'll have 16, negative 16, and negative 16, 16. Number 6 is 3478. The cosine is 12.5 divided by square root of 12.5 square plus 6 square. So that's the value in decimal form. The sine is negative 6 over square root of 12.5 square plus 6 square. That's the equivalent decimal value. The length is 13.865 meters or square root of 12.5 square plus 6 square. Then area E over length times the square of the first term is 0.812744. The product C and S is negative 0.390117. The negatives of these two values here. Then CS, S square, the square of negative 0.42731. Then copy the negatives here. Then copy, copy. So K6 is equal to this. Next, we assemble the, by the way, the fixed forces, area E over length times delta, which is 10 mm because it's positive 10 too long. So we have compression force for the fixed force because the nodal, equivalent nodal force will be opposite to compression, tension. So that's why we have here tension. So at 1, 300 outward, 300 downward. And let's resolve this force into equivalent nodal force into their components. The slope of member 1 is 3, 4. So what 300 at 1, 300 times 4 over 5 times 0.8 to 40 to the right, at 2 to 40 to the left. Then for the vertical, at 1, 300 times 3 over 5, 300 times 0.6, 180 upward, at 2, 180 downward. So that's for the equivalent nodal forces due to fabrication error of member 1, which is too long, 10 mm. Next, for member 5, fixed force for member 5, which is subjected to an increase of temperature of 40 degrees Celsius, beta, delta T 40, area is 1000, E is 200 gigapas, 200 to make it in kilonewtons, and we multiply 1, negative 1. So fixed force of 5 would be 92.8 compression. So that's the fixed force. The equivalent nodal force would be, it should be in tension. So the member should be stretched outward like that. So at 2, 92.8 to the left, and at 4, 92.8 to the right. So these are the equivalent nodal force for member 5, nodal forces for member 5. And because that's already parallel to the x-axis, we don't need to resolve it into components. Then for member 4, which is subjected to temperature reduction of 20 degrees Celsius, so 11.6 beta times 10 to the negative 6, the delta T is negative 20, 1,200 the area, then E 200, then times 1, negative 1. So the fixed force for member 4 will be in tension. So opposite to tension is compression. So we draw member 4, it is subjected to compressive force as its nodal, equivalent nodal forces. So we resolve 55.68 into horizontal and vertical components. The slope of member 4 would be 3 horizontal to 4 vertical. Therefore, the x component of force is 55.68 times 3 over 5 at 1 rightward, at 4 leftward. So 33.408 at 1, then 33.408 leftward at 4, which is not shown because anyway, we don't need to resolve or use the forces at 4 equivalent nodal forces at 4 because 4 is a pin and that node does not move. So whatever is the force acting on that pin, it doesn't matter because it cannot move that pin. So only 1 because 1 will move, will be displaced. So the equivalent Y component of the nodal force at 1 due to temperature reduction of member 4 is negative and it is downward 55.68 times 4 over 5, that's 44.544 downward. So we now compute the equivalent global forces at nodes 1 and 2 only because the rest are fixed, cannot move. And if you look at the truss, it is determinate because there are only 3 degrees of freedom, 2 at node 1 and 1 at node 2. Horizontal only, the vertical is constrained not to move. So F1 therefore, or the horizontal component at 1 of the nodal force at 1 is 240, then plus 33.408. So 33.408 plus 240, that's 273.408 as the nodal force in node 1, the horizontal force in node 1. Then for F2, which is the vertical nodal force at node 1, remember that the truss has already 80 kilonewtons downward load. So the net vertical force at node 1, which is denoted F2, is 180 minus 80, then minus 44.544. So negative 80 plus 180, that's positive 180. Negative 80 is the load, original, downward. Then minus 44.544 for the equivalent nodal force due to temperature reduction of node 4. Then you'll have 55.456 kilonewtons. Then at node 3, remember, at node 2 rather, remember there is a horizontal 50 kilonewton load rightward. Then we have here negative 240 and negative 92.8. So the net nodal force at node 2 horizontally is F3, 50, the original load to the right. Then we have negative 92.8, then negative 240 here. So you'll get negative 282.8 kilonewtons. So we only have to fill in the 3 by 3 matrix, 1, 2, 3, because all the rest have 0 displacements. They are supports. So this is known 3 by 3 and we can easily solve that. So this is the matrix after we assemble. So these are the forces, 273.408, 55, F2 is 55.456, F3 is negative 282.8. Then these are the values of the cells. So there was 1, 1 in member 1 there, plus in member 2, there's no 1, 1 here. Here we have 25, then plus 11.52, and there's none here. So the result is 273.408. Then 55.72 for 1, 1. Then we have row 1, column 2. There was row 1, column 2 in the preceding slide. Then we have minus 15.23, none, none. So therefore, you have negative 0.96. Then 2, 1, negative 0.96 also. For 3, 1, there was 3, 1 there, or 1, 3. Then here, there's none. Here, there's none. There's none. So therefore, you copy the value of 1, 3 in the cell of member 1. It was negative 19.2. So in 3, 1, negative 19.2 also. Then 2, 2. 2, 2 in member 1 plus 2, 2 here, which is 20.48. Then there's none. There's none. 2, 2 here is 0. Then there's no 2, 2 here. So it will give us 31.28. Then 2, 3, 2, 3 in member 1. There's no 2, 3 here. 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 So this is just the 2, 3 of member 1. So 3, 2 is also negative 14.4. And finally, 3, 3. We have 3, 3 of member 1. Then plus 0 here. There's none. There's none. Then there's none. So the result is 35.20. So for 20.48 plus 2, 2 of member 1 is 35.2. So solving for the global displacements U1, U2, U3. So it is equal to the inverse of this matrix multiplied by this global forces column. So U1, U2, U3 is equal to, because we can use your calculator here directly, so I directly solve the values 2.3287, negative 1.564, and negative 7.4037 mm. That's for displacement. Then for the member forces, P1, P2, P3, P4 for member 1. So we have area E over length times the cosine of member 1, negative 0.8. The sine is negative 0.6. Then the negatives of negative 0.8, negative 0.6, 0, 0, 0. Then the negatives of row 1 multiplied by the displacements, 2.3287, negative 1.564, negative 7.4037, then U40. Then plus the fixed and forces, 300 and negative 300, remember, for member 1, due to temperature, due to fabrication error. And you'll get here 94.5744 and negative 94.5744. So member 1 is in compression. Remember how to expand this? Negative 0.8 times 2.3287 plus negative 0.6 times negative 1.564 plus 0.8 times negative 7.4037 plus 0 times this value here, then plus 300, that will be the value here. Then you just make sure that the first calculation is correct. You don't need to compute the second value because it is just the negative of the first value. Because the second value is negative, member 1 is in compression. For member, this is member 4, I think. So the area is 1,200, E200, length 7,500, then the cosine of member 4.6, the sine negative 0.2, the negative 0, 0, 0, the negative of row 1, and 0, 0, 0 times the displacement U1, U2, U7, which is 0, U8, which is 0, plus the fixed and force of member 4, negative 55.68, remember. Member 4 is in the fixed and force will be tension on negative 55.68 and 55.68. So 0.6 times 2.3287 plus negative 0.8 times negative 1.564, just these two because 0.60, 0.800 times this value here, then plus negative 55.68 would be equal to 29.0694. So the second should be negative 29.0694. So member 4 is in compression. Then this is member 3, 4, 7, 8. This is member 4. Member 5 rather. So area 1000 times 200 over length. Then the cosine is 1, the sine is 0, so negative 1, 0, 0. Then the negatives of the first row, 0. Times U3 is negative 7.4037, then the rest 0, plus fixed and force of member 4, 92.8, negative 92.8. Remember, it was in compression. So 1 times negative 7.4037 only because the rest will be 0 times this value plus 92.8. So member 4 is, we have negative 25.6592, 25.6592. So member 4 is in tension. 25.6592 would be the force. Then that's member 5 rather. This is member 2. So show that member 2 is 0 using the above calculations. Member 6 is also expected 0. So member 6 is expected 0. The reason for member 2 to be expected 0 because member 2 is vertical and there's no displacement along the vertical for member 2. That's why we expect it is 0. Member 6 is bounded by hinges or pins, and the pins do not move because these are translation with respect to x and y are restrained restrained. So that's why there's no movement. So therefore, there will be no displacement for member 6. So member 6 is also expected 0. You can check this by using the formulas, same formulas above. So 0. The fact that the displacements at 5, 6, 7, and 8 are zeros will give you 0 result. Then member 3 is member 3. The cosine is 1, the sine is 0, so negative 1, and so on. Then multiply by the displacements at 1, 2, 5 is 0, then at 6, U6 is 0 also. Then there's no fixed end force in member 3, so automatic. The result is 1 times 2.3287, just it, then times this value. So you'll get 58.2175, then negative 58.2175. So member 3 is in compression. So number 3 is in compression.